you to stay out here because we're now going to continue to explore the value of fundamental science in a panel discussion entitled The Unexpected Contributions of Curiosity. So David, if you want to come and sit down, and if the other panelists want to come out, we're going to seat, it's a rather unique panel. We have 6 Nobel laureates here, and we're going to seat them in alphabetical order, rather in a school-like way. So please, come out. Stephen, you're here. Have to work this out. David, if I'm getting it right, I'm probably getting the alphabetical order. Come and sit down, please. I think we have Alan Higa and Carlo Rubbia in the audience, so would you like to come up to the stage? Good. Good. I can't work out what alphabetical order is. Can you, Robert? Oh, it doesn't matter. Here you go. Thank you. Mario? Okay. And Carlo here, please. So, thank you, sir. So, of course, please. Oh, no, you're right. You have your microphone. Please have a seat. So, I'll hand over the panel in a second, but I just wanted to say that, Stephen Chu, David Gross, Alan Higa, Hartmut Mikkel, Mario Molina, and Carlo Rubbia were, of course, all awarded their Nobel Prizes for fundamental research, which was not directly connected with the energy questions we're discussing today. But I think it's safe to say that they are 6 of among the, say, 8 or 9 Nobel laureates in the world today who are most actively involved in discussing the future of energy. So we're extremely privileged to have them with us today. And Robbert Dijkgraaf, who is the director of the Institute for Advanced Study at Princeton, has very kindly agreed to moderate this panel on the unexpected contributions of curiosity. So over to you. Thank you.
Thank you, Adam, for this introduction, and David for the wonderful speech introducing this subject. I think actually it's quite an interesting experiment to have this critical mass of laureates together. I'm almost thinking that they might disappear in a black hole. Too much talent brought together. But I think actually it's also great that we are addressing a topic that in some sense even larger than the topic of energy, where the Nobel Dialogue Week is dedicated to today. The cause of basic research, its position at this very moment, as David indicated, at the same time perhaps research that is responsible to many of the issues that we are confronted with, but also definitely part of the solution. And actually, the first director of my own institute, Abram Flexner, he wrote in the 1920s a beautiful essay. The title was The Usefulness of Useless Knowledge. And I think that title still captures a lot that we will be discussing today. It also tells us that this topic has been around with us for a long time. Tremendous opportunity to have some discussion among you, but I first want to have the other 5 panelists to give the occasion for some brief opening remarks, and we do just this in random, that is to say alphabetical order. And Steve Chu, can I ask you to say a few words?
Well, picking up from the theme of curiosity-driven research and what it leads to, I can draw from my own experiences. For example, when I was cooling and trapping atoms with light, I knew of one application that I was going to head for, and that is when the atoms were cold, you can make better atomic clocks. Atomic clocks are the basis for the most accurate measurements in all of science, and so it was a well-known target. But after me and my colleagues and also other groups around the world discovered that this was a very useful technology, it led to many things that were not anticipated. For example, in my group, it led to a new way of splitting the atom apart, bringing it back together to form a very precise measurement tool. It's called an atom interferometer. Little did I suspect years later that this interferometric measure of gravity would actually will be used and is being used right now, not in this particular form, but likely to be used to actually measure, and I'll talk about a little bit, environmental changes in the Earth. Measuring gravity tells you whether glaciers are shrinking or growing. It tells you about water tables in the Earth. Totally unexpected. The impact on biology was also totally unexpected. When I got to Stanford, we had held on to atoms, we held on to single cells with light. And when I got to Stanford, I said, could we hold on to individual molecules? And if we could, what could we do with it? And that led to an explosion into a different field, single molecule research that is continues to gather strength after almost 3 decades. Brought me into biology and into biomedicine, and now the majority of my time is actually spent in biology, biomedicine, when I'm not thinking about energy.
Terrific. And how good to realize at this moment that all of you, often we are in these discussions about basic research, but we do realize that all of you made this tremendous contribution. It's really your personal experience, actually, that are in some sense putting as evidence here on the table. Professor Dijkgraaf, what your thoughts about this topic?
I remember sitting in my office, a discussion with a young postdoc. We had been, of course, studying the optical properties of semiconducting polymers, the discovery for which we were rewarded with the Nobel Prize. We'd been studying those for many years then. And then out came the Fullerenes, the great discovery of Smalley, Curl, and Croteau. And just literally out of curiosity, what would happen if we mixed them? Mm-hmm. I mean, it was almost as naive and simple as that. Did not have a clear idea of where we were going. So we just did it. And we discovered ultra-fast electron transfer, that you could get electron transfer in a time scale 4 orders of magnitude faster than the first step in photosynthesis. There's no competing reaction that goes that fast. So we saw that as the basis for making a solar cell. And we were making solar cells, plastic solar cells. We're now up to 12%, not good enough. But we see the way to, I know what's wrong, I know what to fix. We'll be at 20%.
And can you just explain how long was the time period from, say, the first idea to where you're right now with these?
20 years, 22 years.
Yeah. Which is even...
Science goes slowly.
Relatively short compared to the 100-year anniversaries that Dave was mentioning.
But, scientists should never lose one's nerve to try something new, and never lose one's curiosity.
Thank you, Professor Michael. And perhaps you have also some advice to young researchers that are looking at our discussion here.
Actually, we are talking about curiosity, and I think we as scientists should be pretty grateful to society that it allows us to do our basic research. Mm-hmm. And we are like little children. Little children like to explore everything, find out how it works, and we are allowed to be little children despite the fact that we are getting old. And if we see, of course, we had already beautiful examples for the values of basic research presented by David Gross, and I simply can, of course, transistors and lasers, everything which came out of that with great importance. What I think, of course, the basic applications will come out from the basic research in chemistry and physics, also in medicine, in biomedicine. But in biomedicine, the way to the application is much, much shorter, because when you discover a new protein and its function, you can identify the disease relation, you can try to activate or to block this protein and to cure the diseases. So the way for application is pretty short in biomedicine. Mm-hmm. But there are other disciplines where there is no application. I like to read about archaeology. I like to read paleontology, and I'm particularly impressed by sequencing the DNA of bones, which are now examples 800,000 years old, a frozen bone in Alaska, and there are human bones from Spain, where more than 100,000 years old, and you can do the DNA sequencing and deduce, find answers to questions about the evolution of the human being. Very important, but no application. And I also think astronomy is very nice. but there is not much application. And I was pretty much surprised recently about the discovery that new stars are born in the neighborhood of black holes. And I think this discovery will give the theoretical physicists a headache. And, and I wonder with what kind of explanations they will come up.
Well, thank you also for highlighting the fact that applications can be beyond simple, economical or societal. They could be cultural, just our understanding in the world. David, you wanted to respond?
I just wanted to say that radioactive dating, of course, was an application of radioactivity discovered totally accidentally, and many Nobel Prizes were awarded for that.
And of course, a very important field for getting Nobel Prize is method development. And if you look back, probably at least 1/3, maybe even more than 1/3, have been awarded for the development of novel technologies, novel methods. And if you want to get a Nobel Prize as a young student, you should go into method development. Your chance is much higher. And if you look for serendipity, difficulty.
Yes.
If you are the lucky person, you have many other people. So method development, highest chance.
I feel we are almost naturally going into your field, Professor Molina, with deep time and the future. What are your thoughts about curiosity and basic research?
Well, first, just like my colleague Hartmut, even when I was a child, 10, 11 years old, it was curiosity that really made me sort of love science. I was fascinated with science. But then eventually, after finishing studies and so on and so forth, I stumbled across a problem with my colleague Sherry Rowland, really out of pure curiosity. What happens to certain industrial chemicals that were piling up in the atmosphere? If nothing else, I thought, gee, it might be just bad manners just to use the atmosphere as a waste dump. But of course, we did not foresee, and what we found, starting with this curiosity question, is that these compounds that were miracle chemicals, they were developed because they were extremely stable to replace toxic refrigerants. But that's the reason why they could go all the way to the stratosphere and affect the ozone layer. But maybe what I want to stress is that curiosity is, of course, so important. We heard all about it in marvelous ways. But the complement is also terribly important. Applied science, applied research, and to follow, again, my own experience. After we discovered that this was potentially quite nasty, in fact, there was additional research that proved that. But then we had to work first with industry. They developed other chemicals that was very much applied research, but also with economists. Maybe that's not a science, according with my colleague David, but it can be rational nevertheless, and it can be terribly important, and politics. And all this led to the Montreal Protocol, which essentially solved the problem of the stratospheric.
You have been, in some sense, extremely fortunate that you had both a wonderful basic discovery, but you also were part of a solution, I mean, which in many ways is seen as a model for addressing bigger issues. Your personal involvement all the way through, was that an important ingredient?
So, well, an important ingredient was to keep track, although the research itself, the science leading to worries about stratospheric ozone depletion, that occurred very fast, but then it took literally decades before the solution actually was at hand. But it gives me hope. That's the only other global environmental problem that has really happened very clearly, and climate change is because of that very much connected. But I see very important analogies, and but here again, more from the applied portion, perhaps having some difference with some of the conclusions this morning, at least with some of the panels. I think economics here is terribly important because just like in the case of stratospheric ozone depletion, some of the best models that I know of, Nick Stearns and others, they tell us it's relatively cheap, 1 or 2% of global GDP. So I differ that it's very costly. It's certainly much cheaper than to pay for the consequences. Okay? And it's something that can be done, but politics is in between. So here, we scientists have not done a good job of communicating the nature of the problem, because society at large still doubts whether science is pro or con. But in any event, we have much to learn from success stories, and we have much to learn from working as scientists, but really learning, it's partly curiosity as well, but learning other disciplines, politics, how society functions, economics, and so on. That's why I'm optimistic. I think some of the problems we know now, like in the United States, the Congress that would not ratify the treaty at the moment, I believe sooner or later, in a few years, they will no longer live in the age of astrology, and hence rationality will come with us, and we will begin to solve a problem, putting a price on emissions. So we just, as scientists, we just have to keep working very hard. We have to be patient, and we've shown that that can be done.
Thank you. And finally, Professor Rubio, I think experimental particle physics, it's sometimes seen as a field perhaps most removed from everyday problems.
Particle physics, even worse.
Yes. What's your view on
the
role of curiosity in basic research?
I want to say a lot of things already been said. I mean, we heard a nice presentation before, then the presentation. So I will try to concentrate on those things which have somehow left behind. And of course, my interest is the unexpected contribution to curiosity as a theme. And I think that curiosity is one of the deepest instincts of the human mind. It is curiosity which has pushed the whole process of evolution from the beginning to today. It's curiosity which has permitted us to discover the moon, for instance. Nothing else but curiosity. The best example of curiosity is a child. A child has a toy. And this is interesting for him, essentially because it attracts his curiosity, up to the point to break it at a certain moment to understand how it works. Understand how it's made is often more important than the possibility to play with it. This is one of the most important properties of curiosity, to risk, to accept, to lose something which belongs to the child in order to respond to the necessity and the courage to comprehend the effect. Now, it is quite clear that the man has the need to comprehend, to understand, but he also wants to invent and to construct for himself and for the others. And this is what construction is, what's called technology. But in order to construct, we have to know and to preview, foresee. And from that, then essentially a universal bind between science and technology, between knowledge and invention. There is an important connection between the technological evolution of a modern society and the corresponding biological evolution. Any new development driven by innovation replaced the old one in this perfect analogy with the biological evolution, in which a new development replaced the existing element. It is clear that we are in front of one important element, which is today the globalization. And globalization is going to change a lot of things. A lot of things will happen. And many people are concerned about the fact that the globalization may bring a uniformization of all activity. Everybody becomes equal, no matter what happens. But this is, of course, completely wrong. Because this diversification, it's a strong generator of new ideas and new solutions. And in fact, I believe that the diversification between cultural roots of each of us will be the generator of new ideas and innovation. It's just because of the fact that everybody is different from each other that we get the differences which bring the new. There is a place for every one of us in the world. It's our job, our responsibility to acquire it. Let me say one more thing because I finished. That's the question of the ability of mankind to accept such a quick variation dominated by novel technologies. It's most likely that one part of our society may remain behind this process of evolution. And therefore, you are going to have the risk of a new generation of technological illiterate which will add themselves to the normal illiterate and will cause big differences, big problems for the mankind of us. And that implies one thing, education and formation, which are absolutely fundamental, associated with science, because without them, we'll not be able to ensure a uniformity within the globalization.
Thank you for these remarks, and I think actually would be probably the worst panel to have a serious disagreement about the value of basic research. But you pointed out, several things were pointed out that would some sense would encourage more basic research. The globalization, the technological aspects, the understanding of the role of science. On the other hand, people might also argue that we are not living in the best of times for basic research. So if I just can see, what are the ideas that you have that could possibly change, or how should we build an ecosystem that is maximally supportive of basic research and talent? And what are your thoughts about this? Are we moving in the right direction?
Well, I think it's neither one or the other. We should always let basic research thrive. But there are certain instances, you know, I spent 9 years at Bell Laboratories. Most of the research there was not basic research. But what was true, it was if someone found something interesting, management would say, go, run with it. There were certainly a number of us who would say, let us go and do whatever interests you. But most of the work was actually targeted. And if you think of the stupendous things that came out of Bell Laboratories, for example, just the invention of information theory.
Yes.
That had something behind it. They really wanted to know how to send signals down a noisy line. The invention of transistor was very directed. Those vacuum tubes were burning out. They wanted a solid state amplifier and solid state switch. And so it was targeted research.
But that Bell Labs isn't no longer with us, right?
But I'm just speaking in terms of basic research and applied research,
Yes.
that they both really do go hand in hand.
Yes.
But other things can't be targeted. Discovery of superconductivity, things of that nature, the discovery of quantum mechanics. You've just got to let that happen. But once you have these tools, you can actually use those. So regardless of whether there can be a Bell Labs today or not, I think it's not one or the other. You certainly have to let basic research thrive.
But it's part of this much bigger
Yes.
chain.
Yeah,
David.
but I think the stimulus for asking new questions can be both, come from obvious problems, targeted research, and from just exploration in the dark. What is really needed, however, and was correct at Bell Labs, was true in Bell Labs and in many of the institutions that we all have belonged to, is freedom. Freedom to pursue those ideas, sort of not thinking about immediate return and as Energy Secretary, bureaucracy. The biggest enemy I see locally for basic sciences in the United States is not so much the level of support, the dollar amount, but the fact that it is not cheap and therefore must be supported. Its benefits are largely social benefits, which must be supported by the governments and not going to be supported by private. And that does lead to inevitable bureaucracies, which are anathema to basic research.
Professor Rubio.
Well, I just want to mention, sorry, I'm losing my voice, a simple argument, namely that out of the 7 billion people which are today alive, you can compare them with the totality of the people which ever live on Earth, from the beginning, from the day in which we came down from the tree, and this is about 70 million. So about 10% of the population ever lived in the history of mankind is alive today. And this is an exceptional condition which changes totally the problems and the solutions. Because to realize that we have, if you add to that the fact that we now are completely globalized, the communication exists, we are connected to it, the connectivity is increased to a tremendous amount. 10% of the world population ever existed with the connectivity we have today must be able to solve the problems that is ahead of us.
Would you argue that, I mean, all of you did research in wonderful environments. The present generation, would they have these kind of opportunities?
We have a big, enormous responsibility, but also enormous opportunity. Because these are unique conditions which never, the history of mankind was never there. We never be having no war, no big growing, very clear growing level of living. We strive, presumably we are solving most of our problems. But the important fact is that we also are also interconnected, which have never been so much in the past. All those things are clearly an enormous opportunity for us to come up with a positive statement. So I would be very optimistic about the possibility that mankind will, one way or the other, use this challenge, use this solution, and come up to some kind of situation which will be very different than the one we are today. Because changes will be enormous, but they have to be handled. But I think we'll be able to handle them.
Professor Molina, and then Professor.
Yes, what I believe is also quite clear, coming back to our friends, the economists. Just empirically, the countries whose economies are doing very well and have done very well have invested a lot in basic science and technology. That's just empirical. Now, we could try to ask why. Obviously, innovation is a crucial part of that. That's the word in the United States. If you start cutting on this type of funds.
But
then,
sometimes with long time horizons.
yes,
They would say that
but
we
But
have
that's
to look
crucial.
50, 100 years.
I mean, we were just listening the 100th anniversary of some crucial discoveries. If we start having short-term horizons, then we are not doing justice to whatever we were inheriting from earlier scientists. But there's another very important fact, which is just, again, very empirical, and that's education. A lot of research is carried out in universities, and the best research is carried out in connection, well, students carried out with faculty. Many of us Nobel Prize winners have students and so on. So it's another way to guarantee the quality of education. So there are so many factors. You could call them empirical, some short-term, some long-term. Hey, but most people invest in educating their children, even their grandchildren. They're not going to see what happens to that in 1 or 2 generations. But nobody thinks, no, let them worry about it. So it's obvious that to me, that we should keep investing to continue with economic growth, but also to guarantee that it will be there.
Thank you for highlighting that it's very human to think of the long term.
The human value. Yes. That's not science. That comes from human values.
Alan.
I wanted to return to the comment that you made about communication.
Yes.
When I was very young, undergraduate, and trying to decide what I should do with my life, I went to a physics professor whom I greatly respected, and very naively asked him, what does it take to be successful as a physicist? And he answered me by saying, how are your grades in English? And I was surprised. And he went on, and he said, communication is the whole thing. If you don't get your results out, that people can understand them, then it's meaningless. But now I want to take it to the next point, because we do well as scientists communicating among ourselves. We go to meetings, we publish our papers, we read even some of them. But we do not, I would say empirically, we do not communicate well enough with the governments.
Well, I think this is an extremely important point, because there were already things said about economists, politicians, but there's also the general public in some sense. I mean, the voters or consumers.
Yes.
I think certainly very appropriate today, which is very much also about a dialogue. how we can kind of speak to that bigger constituency. So are we able to explain the role of curiosity in basic science? How can we connect? What can we do better in terms of reaching out?
I want to make a very short remark.
Yes.
I think we should all learn from Machiavelli. Machiavelli already had all the answers to these problems. And he says the political person which has advice before the others is the one going to be the winner. Mm-hmm. Because when you see something everybody understands, it's too late to find a cure. And the cure is only possible, only a few people know it. Seems to me this is an important message, that we should transmit to the political people the necessity to realize things before the public follows them. They have to be ahead of them.
Have to be ahead.
This is what Machiavelli said, it's still true today.
They might read ahead, yes. David.
Well, I think in order to engage and convince the public or society of the importance of curiosity in basic science, most important thing we could do is make sure that their curiosity is not stifled in K to 12 in school.
It's often switched off, right?
It's often, you know.
But there is another point which seems to be important. Most of the ideas and problems ahead of us are ideas of long range. They represent developing cancer development or any development we think of is 20, 30, 40 years' time, over which you need a steady, constant support. Yes. Unfortunately, the political world is localized to the time period, which is much shorter than that. Mm-hmm. And 3 or 4 years for scientific development, new ideas is very short, it's too short. Not only that, but most of the politicians are concentrating themselves, allow me to say, much more to the mass media, which have even a time scale, which is even shorter, rather than worrying about the necessity of taking a steady condition which will persist from one person to one system to the next.
I see many remarks. You get all your first. Yes, David, and then Professor Mika.
You were in the midst to finish my point. Yes, which was that unless we improve education of science in basic education, we're never going to be able to convince the general public of the truth of our observations. We're just going to find some gimmick, and other people can find those gimmicks who are misinformed. Yes. And we see that, for example, in the U.S. Congress. I mean, it is amazing how ill-informed the representatives of the people are. I can't believe that those ill-informed people got a good science education in schools. They couldn't.
You have lots of experience. I'll return to you in a moment. Professor Mika.
Well, that's the most important point, that the general public also needs a good basic scientific knowledge. Without that, we cannot communicate. Right. If I'm an Indian and I talk to people and they don't know what an amino acid is, I cannot talk about biomedicine. So there is clearly basic knowledge. If people don't know what an electron is, I'm lost. So I get questions, what is the color of an electron? And things like this, which is so, of course, difficult to answer. But I want to turn to a different issue. In order to make research, what about the structure of a research system should be? And for that, we need actually positions for scientists also when they are 40 or 50. We don't only need postdocs. We have to give the PhD students and the postdocs a perspective in the scientific research system, and we do not have this in appropriate amount in Europe. I think the United States is better, but in Germany it's not good, because the chance that you can stay in research for a PhD student is maybe 2 or 3%.
So also long-term thinking for research careers.
Long-term thinking for research careers is very, very important. We clearly have to improve that.
I just want to turn to you, Steve, because you're uniquely qualified that with your experience as Secretary of Energy, you have seen this debate about science policy, in particular, on the interface of energy from both sides. So,
yes,
any wise lessons there to be shared with us?
I hate to be pessimistic, but I don't think a good K through 12 education is the only thing that's needed. I think the debate in Washington today, a major debate, is whether climate change is real. Is it really happening? What's the chance it was caused by humans? Now, to most scientists who pay close attention to the developments in the science, it is not a debate. It is the same as saying that the medical community was debating that there is a very strong correlation between cigarette smoking and lung cancer. But there are a lot of people, at least out there, saying we're not absolutely sure, there's no real proof, it's going to be very expensive, so why do this if there's no real proof? And the issue is much more complicated than that. A lot has to do with, and this goes back to something which Gregory Peck said in To Kill a Mockingbird. In order to understand someone, you have to walk around in their shoes.
Mm-hmm.
And if you're walking around in the shoes of someone who wants to get reelected,
Yes.
and there are companies that say, we will be glad to support your reelection, but here's some talking points that we want you to think about. And this does influence people. The real issue, though, is in the end, the data has to win out. The data really has to say, okay, this is really happening. But in many cases, and the most discouraging thing is, some of the opponents aren't skeptical that climate is changing. They're actually trying to defund those instruments like satellites that take the data. And
so they prevent almost the evidence being shown.
Yes, absolutely. And so it's not that they're skeptical, they just don't want to know the answer. And so I think in the end,
They don't want to know because they already know.
They already know the answer. I think it's like after tobacco companies were doing research in the 40s and 50s, after that they began to know the answer, so they defunded their own research. Okay, but to defund the research of the Department of Energy, of NASA, of NOAA, that is getting a little bit beyond the pale. I think the American public has to know that we want to know the data, we want to know the answer, and sooner is better than later. And this is something that's very important. It's not a matter of trying to convince some recalcitrant congressmen. In the end, it was the American public that said to Congress,
Yes.
cigarette smoking appears to be dangerous. We're going to have to limit advertisements. Then the government followed.
So again, I think that might be a good lesson for, in fact, what we are doing here today. We are running out of time, so just want to thank you for being particularly so cheerful. I think we're just, although there are serious problems here, I'm actually convinced that in 100 years we have many, many anniversaries of things being discovered right as we speak. So thank you very much for this lively discussion. Thank you. You'll just continue.
Now, before we break for lunch and move into the part of the program that's entirely devoted to discussion panels involving you, the audience, as well, I believe that Steve Chu wants to set us all a challenge to take with us through the rest of the day. So,
Okay.
Steve, the platform is yours.
I don't know if I'm setting someone a challenge, but let me begin and hope I'm already beginning with minus 2.3 minutes, so I'll just add it. All right, as I just said in my other remarks, here's some data. This is data from 1800 to 2011. This is the average land temperature in the world, and you notice it's very noisy. We don't understand a lot of these bumps and wiggles, and I don't understand this. Oh, here it is. We don't understand these plateaus in the temperature rise. There's a plateau here, there's a big plateau here. We don't understand these little wiggles, but we do understand over a long period of time that as long as the energy hitting the Earth has not changed, average over a long period of time, because of the so-called greenhouse gas effect, the temperature has to rise. I should also point out that 3/4 of this temperature rise has occurred only in the last 35 or so years. And also the amount of the temperature rise is quite modest. It's only about 0.8 degrees centigrade. But with such a modest temperature rise, it's not uniform, and these are two pictures taken in August of 1941 in August 2004 of a glacier in Alaska, and they look quite a bit different. And I'm sure in northern latitudes, like Sweden, you also have similar images of your own. But this is true in the northern latitudes all around the world. There's also issues having to do with hot spells. This is a heat wave in 2003, and perhaps many people don't realize that 52,000 people in Europe had died during this August heat wave. 52,000 died during that. There was another heat wave in Moscow several years later. About 15,000 people died. Now, this again is data, and so what I'm going to show you is the temperature variations in the month of June, July, August in the northern hemisphere. And it begins, let's see if I can get it to go. Nope. It should be playing. Maybe someone in the back can get this thing to go. Well, I'm going to move on. But what you would have seen, oh, here we go. What you will see is a Norman distribution. Again, the summer months, June, July, August, and these are the years ticking by. And as the years tick by and they go to the current time period, you see that something has changed. What has changed is what used to be an average temperature over here is now over here, but more importantly, the extremes in temperature have moved over. And in the years 1950 and 1980, what would have been about a 0.14% chance of having an extraordinarily hot day is now an 8% chance of having that extraordinarily hot day. And so it's those real heat waves that are becoming more standard or unusual. So that's another example. Now, let me tell you a little bit about changing glaciers. It turns out there's exquisite ways to measure how glaciers change. This is one of them. These are two precision satellites. As they orbit the Earth, changes in the local gravitational pull of the Earth will perturb the orbits of these satellites. These satellites measure the distance between each other very precisely, to millimeters. And in so doing, you can actually back calculate the change in the acceleration due to gravity in the Earth. And this is a change over Greenland. This happens to be the years 2002 to 2012. And these oscillations are summer, winter, summer, winter. But why is the acceleration due to gravity changing, decreasing in Greenland? It's because the ice sheet is melting. The precision of this measurement is exquisite. This is the change in the ice sheet over Greenland to 0.2468 millimeters. But right here is that it's shrinking on average and it's accelerating as it shrinks. This is more data of this satellite. This is Greenland. This is the loss of ice mass in Greenland, mostly in the southern part of Greenland. These are satellites that cover the entire globe. Antarctica was expected to actually gain in ice. There's a little gain here, but there's serious loss here. The reason it was expected to gain was there's expected to be more precipitation, and it was so cold it wasn't going to melt, and yet it turned out not to be true. This is the Tibetan Plateau. There's loss of ice mass here. There's a little gain in here. There's not much glacier here. This is the loss of a major water table in India. So these precision measurements actually allow you to measure changes in water tables as well as changes in ice mass. And as I mentioned in the discussion period before, some work I had done beginning in 1991, being able to use laser-cooled atoms to drop them and measure the local gravitational acceleration very exquisitely. That tool is now being designed to be put up in a satellite that could have about 100 times better resolution than these satellites. This is very important because it's important that we further measure not only shrinking glaciers, but we have to understand how the water tables around the world are changing. Because in many parts of the world, including the United States, the water tables west of the Mississippi are shrinking. And this is of great concern. Here's some more data of changes. Again, in this period where the most significant temperature rises occurred, 1980 to 2012. This is data taken by a reinsurance company. That is to say, insurance companies that insure insurance companies. If there's a major flood, a major hurricane, the insurance companies may not have enough assets to pay back all the claims, so they take out insurance. So Munich Re insures those insurance companies, and they plot losses due to earthquakes, storms, floods, droughts, fires, crop failures. And you see that over this period of time, although it's very, very noisy, and this is only part of 1 year, you see that there's a trend line rising in the number of forest fires, droughts, hurricanes, whatever. These are the losses, both insured and uninsured, and the trend line is going now to about $200 billion a year, but this is actually insured losses that are counted in a certain way. If there's a large storm, like Hurricane Sandy had a flood, you've closed your doors as small business for 1 month, you can't make your repairs, your business vanishes. That is not included in the loss. It's only a property damage loss. In flood insurance in the United States, it's backstopped by the federal government. When the insurance companies can't pay for it, the federal government steps in and says, okay, we'll backstop the premium. The backstopping is now at $26 billion. The interest on $26 billion is not covered in these losses. It will be never recovered in premiums. $26 billion in interest alone is just now carried on as part of the national debt. And the next big storm, it adds a little more, and so on. So that's what's happening. If you look now in the catastrophes around the world since 1950, you look at all the dates, and you see, golly, if you start the record bookkeeping in 1950, all but one, 1992, are in the decade, the years 2000. All the ones boxed in red are weather-related events. The rest are earthquakes, or earthquake tsunami. And so something strange has been happening over the last 35 years. And so I'm just pointing out that although the climate models are getting better and better, they're still not to the point where they can tell you this year will be a bad hurricane year, this will be bad tornado season, and so on. But nevertheless, if you use an analogy to science, in the 50s, 60s, and even today, medical science cannot tell you if you start smoking cigarettes that you will get lung cancer. We can only tell you there's a 30% higher chance you will get lung cancer than if you did not smoke. So in each individual, we can't tell you that. So I liken it to climate epidemiology. So this is health epidemiology. And you see that this is the United States, this is men smoking from 1900 to 2005. The average smoking in the United States was virtually nil at the beginning of the 20th century. It rose precipitously. The number of deaths due to lung cancer also rose precipitously, but notice there's about a 20-year delay. Around the 50s and 60s, it became clear that cigarette smoking was dangerous to your health, not only for lung cancer and emphysema, but also for heart ailments. And a massive campaign discouraged advertising, forbid children under the age of 18 to buy cigarettes. The amount of smoking in men went down. 20 years later, the incidence of lung cancer went down. In here, the incidence of smoking among women went up 20 years earlier than this graph. And so here you have something that says, does this prove that cigarette smoking causes cancer? Well, let's just say they're correlated very strongly. Let's just say that rise in the land temperature is seemingly to be very correlated to very lossy events in terms of weather. Now, we only have 35 years. Here's another problem. This is a delay time of 20 years. The delay time between when we put up greenhouse gases and what's the equilibrium temperature is something we don't know. It could be 50 years or it could be 100 years. Why so long? Because it takes about 50 to 100 years, depending on which ocean you're talking about, for the top temperature of the water to mix with the bottom of the ocean, say 2 kilometers deep. When I was in the Gulf of Mexico one hot summer in 2010 trying to help put out an oil spill, the surface of the Gulf of Mexico was 86 degrees Fahrenheit. The bottom, where the oil was leaking, was 2 degrees above freezing. It takes about a half a century for that water to warm up. So in the meantime, the greenhouse gas layer says we're still going to be putting energy into the earth, and since it takes so long for the bottoms of the ocean to heat up, the real damage won't be known, just as the real damage is not known over here. So that makes the problem even a little bit more pressing. So the first law of holes, if you find yourself in a hole, stop digging. Now, the Stone Age came to an end, not for the lack of stones, and the oil age will come to an end, but not for the lack of oil, said by a former Saudi minister. So what am I talking about? We're talking about transitioning to better solutions. And what do I mean by better solutions? Solutions that are economically viable, solutions that are actually have no real downside in terms of our prosperity. And we'll need both energy efficiency and clean energy sources. Very briefly, buildings. We waste tons of energy in buildings. Roughly 40% of the energy in the world is spent heating and lighting buildings. And if you build a new building with good standards that using all the things we know about how to build buildings, for the same price of the building, you can save half the energy. And yet today, it's not being done. Appliances, refrigerator appliances. Everybody felt that if you demanded that an appliance be more efficient, they would cost more money. So here's the open circles and the open squares are before standards. This is the first California standard. This is the cost of owning and operating a refrigerator. This is the cost of the refrigerator. So this is the cost of the electricity plus the refrigerator. This is just a refrigerator. You notice when standards started, and there were 6 standards, 3 in California beginning, and followed by 3 US standards. You noticed how much, every time the number of refrigerators doubled, and this is the price coming down by a certain fraction, you will notice how much the cost of the refrigerator skyrocketed whenever there was a new appliance standard. Well, maybe you don't notice, but it should have been there. We looked at room air conditioners, and lo and behold, you signed, these are after standards, these are before standards. This is the purchase price of the air conditioner. How could putting in standards make the refrigerator or the air conditioner cost less? Same with washing machines, same with central air conditioning. We submitted this paper to a magazine called Science. It was reviewed by economists. Some of them said this is amazing, this data that stretched over 40 years in both Europe and Europe and the United States really is eye-opening. And another person said, no matter what you guys say, the economists are not going to believe this. So maybe they're not scientists. In any case, in terms of efficiency, this is something that Department of Energy is pushing. Can we have electric vehicles or plug-in hybrids? But something that could be mass marketed, something that has a sensible range where there is no range anxiety, but without subsidy, $24,000, comparable in performance to a $20,000 car. Of course, it really depends on the battery. The rest of the stuff is in hand. The good news is, in 2008, it cost maybe $1,000 per kilowatt hour. By 2012, the cost of the battery went down in half. We have a very ambitious target. Perhaps in another 10 years, can you make the cost of that battery not only going down by a factor of 2, but perhaps a factor of 3? We don't know, but let me just say that there are many, many technologies that we have been following in the Department of Energy, and since I left the department, have been following. And we don't know which will come to fruition. I'm going out of time, so I'm just going to say that battery energy densities are doubling. Well, can they double again? They've dropped in half. Can they drop by another factor of 2? This is happening as we speak. Whether we can get the energy densities of the cathode up, we don't know. But there are at least a half a dozen technologies. They look very good. Wind. It was said before that renewables will always cost more than fossil. I disagree. In the United States, class 3 and 4 sites, the cost of new wind is about a little over 7 cents a kilowatt hour. That's cheaper than anything else except new natural gas, but our new natural gas is based on $3.50 a million BTU, about 1/4 what it is over in Europe. And so it's not far away, and perhaps within a decade, including transmission, including storage, wind will be comparable to new natural gas at $4 to $5 a million BTU. So we're very good on that. Solar, it's actually improving greatly. Right now, solar modules, the production cost of solar modules today is 50 cents a watt. Okay, many of the solar companies have been locked into long-term silicon contracts based on contracts written when there was an over-demand, but right now the current production costs are about 50 cents a watt. Within a decade, you can sell profitably at 50 cents a watt, okay, for production costs, down to 1/10 of what it used to be a decade ago. We need better electronics for distributed energy. This is going along very nicely. A small research program, RPE, the Department of Energy supported, has generated a single transistor that can handle 1 megawatt, 20,000 volts as a prototype. This is going to be absolutely necessary for handling high-powered switching, for electronics and wind turbines, for electronics and electric vehicles, for many, many things like that. We have a company that's claiming they have the chemistry already for batteries at $160 per kilowatt hour. It remains to be seen. They're going to be putting some of these into prototype testing to see if it can really go there. That's having some scalability, but if it turns out the first few turn out to be true, then at least for sure we can get down to $200 a kilowatt hour. It's about $400 a kilowatt hour today. If this is true, then all of a sudden a lot of the day-night shifting of wind and solar will be fine. Now, sometimes the wind doesn't shine, the wind doesn't blow, and the sun doesn't shine for weeks on end, so you will need natural gas backup, but we have that too. These turbines can go 0 to 150 megawatts in 10 minutes. And they're each of them. And so that's the lead you need for when the wind stops blowing and when the sun stops shining. So this is a very, very good complement to renewables. Let me just end by saying this is a sustainability chart, health human index on this axis, and this is an ecological footprint. The richer countries have the wherewithal, without loss of standard of living, to actually use less resources by using them more efficiently and by having more carbon-free energy. But there's something else I need to tell you. What is the sustainability of the Earth? We don't know. Agriculture, grains, the number of grains, rice, wheat, corn, that we grow per acre around the world has increased 5-fold in the last half century. So the real sustainability of the Earth we don't know, but we can say that the richer countries can get down to here without any sacrifice in the standard of living to make headroom for the developing countries over there. And so with that, I just end by quoting an economist, Kuznets, and if you apply it on the y-axis, health, income, education, governance, the governance means rule of law, less corruption, things like that, and you look at environmental issues, you go and as the country develops, there's more and more environmental issues, and finally there's social societal concerns in health and environment emerge, and they have to be melded into business, and then you do the right thing. So I leave with you with this. Where's it written that things have to get bad before they get better? And is it possible that we can learn from the mistakes of our predecessors? I hope it is, because if we don't, then, and if the developing countries follow the path of the developed countries, then we will have a serious problem. Thank you.
Thank you. It's a bit depressing to discover that my approach just inhibits interesting people saying interesting things, but there you go. So hopefully that morning has filled your heads with food for thought that will lead us nicely into what is now going to be a discussion part of the day. let me just tell you what happens now. During lunch, there are several different discussions going on, and you're free to choose whichever you want. And they're all happening downstairs in the E area. So if you go out and then go down the escalators, you'll find lunch down there by those rooms. And then at 2:30, we begin the parallel discussion streams, and you all have signed up for one or other of those streams. And so you just need to find the room where that stream is going on and join it. And those discussions will last for 2 hours, 2 panels in each. Then there'll be another coffee break, and then we're back in here for the final session. So if I could just ask all the panelists involved in any of the lunchtime activities to come to the stage, please, and we'll go back through the backstage area. Then I'd just like to wish you all a very nice lunch. Thank you very much to all of you and all our panelists.